So here's our equation. 2x minus 3 equals 11. To solve my equation, I'm going to start by moving this minus 3. Again, the goal is to isolate the variable, leave this x by itself. So I must move the 2 and the minus 3. I like to move anything that's being added and subtracted first. Not that that's the first step that you have to take. That's the path that I like to go. Um, Properties of equality say whatever I do to one side, I must do to the other. We know that negative 3 plus 3 is giving me 0, leaving me with just the two x's here. Is equal to 11 plus 3 is 14. That means that I now have to isolate this x. I must move the 2. We remember that number and variable next to each other without a symbol means multiplication. Therefore, in order for me to move the 2, I need the inverse operation, which is division. And whatever we do to one side of the equation, I must do to the other, according to the properties of equality. 2 divided by 2 is 1. And 1x is just x. So x is equal to 14 divided by 2, which is 7. I like to check my answer, so I'll go back and substitute the x for a 7. So according to our original equation, it was supposed to be 2 times whatever x is minus 3, and my answer is supposed to be 11. Well, 2 times 7 is 14. 14 minus 3 does come out to be 11. So my answer checks. Using a scale and our virtual manipulatives, on the left side of the equation, I'm supposed to have two x's. So there's 1, 2 of them, and I'm supposed to have 3 negatives. Here are my 3 negatives. On the right side of my equation, sorry about that. On the right side of my equation, I'm supposed to have 11 positives. So there's 10 of them. There's one more for 11. And let me let this know that I need it to be balanced, right? I need to balance my scale here. Now, from here, in the previous examples, on both sides of the equation, we either had positives or negatives, and we were able to just take them off because we had the same kind of thing on both sides and still keep this balance. However, this time I cannot take 3 negatives out of here and 3 negatives out of here because there are no negatives on the right hand side. So what I'm going to focus on this time is making zeros. Like I did here, I made a 0 here. So if we remember from before when we were dealing with integers, I could put a -1 and a +1 together and make a 0. I could dump them in the 0 bucket and it will put them right next to each other to show me how many zeros I have collected so far. So let me put this back. Okay, so if I want to make zeros, the goal is to leave the x's by itself, so I need to move these. That means I need to make these become zeros. So I could put a 1 there and make that one a 0, but notice that my scale is no longer balanced, right? In order to keep it balanced, hey, whatever I do to one side, I must do to the other. Right now it's balanced, but I still have negatives on the left side, so let me keep making zeros. Put that there. And I'm going to place that there. It's now balanced. I still have a negative on there. Here we go. Put another one there. And it's still balanced. And notice that these are zeros. And now I only have the two x's. So I had 10 there, 11 that I started with, 3 more. That's a total of 14, just like we see in our equation over here. From here, I'm going to make 2 equal groups, right? I have 2 x's, so I need 2 equal groups. So let me move things here a little bit. Now, these are each in groups of 5. So I'm going to split it into 2 groups. I'm going to say, hey, that's the top x. This is the bottom x. I see that I have these already in groups of 2, so I'm going to move that up there with the top one, and these 2 with the bottom one. So that means for me that 1x, there we go, kind of, sort of, is equivalent to 7 positives. Right? If I take this out, and I take 7 of these out, this should still be balanced, right? And we can see it that 1x is equal to 7. The third way in which we could solve this is using our counters here in our boxes. So again, I like to use boxes to represent my variable, my unknown. It means I have a box or a container with a certain amount of items inside. I need to determine whether what's inside is positive or negative, so that at the end, I have a total of 11 positive counters. Well, here's something that I know. I know that when I combine some positives with some negatives, that they're going to end up becoming zeros. And I know that when I combine what's in here with these three, I'm supposed to have a total of positive 11. So that means I must have more positives than negatives, right? So, and how many more positives do I need over here than negatives in order to have a total of 11 at the end? Well, I need to be able to combine what's in here with these -3 and end up with positives. So I know that I'm going to need at least 3 extra ones, extra positives currently than what I have over here in order for them to make a zero here, right? So if I have 3 extra ones here, I'm going to need 3 extra ones here. And for now, I'm going to put them down here so we can see that these are the extra ones that I put on there. We know that this makes a 0. We know that this makes a 0. We know that this makes a 0. That means that inside these two boxes, I must have enough for a total of 14 counters. So that again, when they're combined with these three, I have a total of positive 11 like I did at the beginning. Okay. So in order for me to have these positive 14, I must have positive counters on the inside, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, because that's how many I have here. Well, if I think about it, right, I end up with 7 in each box. Well, 7 plus 7 is 14. Let me put these back over here to represent the original one, right? So 14 positives combined with 3 negatives will end up giving me 11 positives, which was my original. That means that each one of my boxes here will need to have 7 positives in there.